uniform distributions, usually we can make shapes like a rectangle, something like this. We do want the area of the entire shape to be 1. So, like, see, these are our random variables. This just happens to be time waiting in minutes. And there's a probability of 0.2 for 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. So there's a probability of, there's a 20% chance you have to wait for 1 minute, 2 minutes, 3 minutes. So what you could do, if you have a uniform distribution like this, let's say that you wanted to know the probability of waiting 2 minutes or less. It's really neat how you can find that probability just using regular old geometry. So if I want to know the probability that, let's say my wait time x is less than 2 minutes, then I could make a shape right here. Okay, and we all remember, hopefully, that if we have a rectangle, that to find the area of a rectangle, you just say length times width. So if I want to know the probability that I would have to wait less than 2 minutes, or 2 minutes or less, then I just find the area of this shape. Now, it may look like a square up here, but keep in mind that there's a different scale on the y-axis, or the vertical axis, than there is on the x-axis, or the horizontal axis. So the probability x is less than 2, you say 2 units times 0.2. All right, so 2 times 0.2, that would be 0.4, or 40%. So there's a 40% chance that you would wait 2 minutes or less. So kind of neat how you can tie geometry into something real simple like that, into a, I guess, kind of a harder topic, probability. That's a uniform distribution. All right, your book says a uniform distribution, a continuous random variable has a uniform distribution if its values are, here's the main point. Here's the main part here. Spread evenly over the range of possibilities. The graph of uniform distribution results in a rectangular shape. Okay. The density curve. A density curve is a graph of a continuous probability distribution. It must follow the following properties. The total area under the curve must be equal to 1. Very important. Every point on the curve must have a vertical height that is 0 or greater. That's because that vertical height would be a height that would be in the, or under the curve here. So if this represented a density function, notice there's nothing below this x-axis. Everything would correspond to some height that's positive up here. Okay. Don't read too much into that, though. Area and probability. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. Everybody knows probability can't be less than 0, probability can't be greater than 1. The total probability of an event, the probability of A and not A, is equal to 1. Okay? So I can use that to help me figure out probabilities that certain things will happen if I have some general information. Now, if we have a uniform distribution, like here, this is the same thing I was showing you earlier with the minutes. If I wanted to know, look at this, find the probability that a randomly selected voltage is greater than 124.5 volts. So all you do is go to 124.5 and then see how far to the right you can go, because it wanted to know the probability it's greater than. What does greater than mean? On a number line, it means to the right. Less than would mean to the left. Well, we're going to use that concept a lot in here. So you need to go ahead and associate. Greater than means to the right, less than means to the left. All right, but here, to find the probability that a randomly selected voltage would be greater than 124.5 volts, that's 0.5 units there, and the probability is 0.5. So 0.5 times 0.5, 0.25. So the probability is 0.25 or 25% chance that a randomly selected voltage would be greater than 124.5. Now this is related to some other problem, not all voltages in general, just some application problem. All right, here's the standard normal distribution. The area is equal to 1, the mean is equal to 0, and the standard deviation is equal to 1. Now, not all distributions are standard normal distributions, because think about sets of data. Not all sets of data are equal, the mean is equal to 0. Okay? So this would have to be something that had data values that were positive and negative, so that whenever you took the average, you got 0. That is a standard normal distribution. I guess the most important part is standard. If it didn't have standard in front of it, the mean's not equal to 0 and the standard deviation is not equal to 1. Do you recall in previous chapters what we know about standard deviation, what it actually means? Remember that? Remember everything within one standard deviation of the mean, that would be to the right or to the left. So all these data values here, that makes up about 67% of all data items. If you go 2 standard deviations from the mean to the left or to the right, anybody remember that? It was like 97%. So the standard deviation being 1 and the mean being 0 is what makes this so simple. And if we can use this simple example, and you can understand that, then hopefully you can understand a little more complicated example as well. All right? So to find probabilities, either we're going to be given the z-scores, or maybe we're going to be given the information to find the z-scores. Okay? So if we know z-scores, though, and do you remember what a z-score is? This is back a couple of sections. A z-score is x minus mu over sigma. That's the population z-score. Mu is the mean. Sigma is the standard deviation. X is some value that we're looking at. Now, if we're given the standard deviation, of course, you don't have to calculate it. But in a lot of these problems, you have to calculate the z-score. Now, if it's a standard, look up here at this formula. If it's a standard normal distribution, what's the mean? 0. What are you dividing by? What's the standard deviation? 1. So you end up with just x divided by 1, or x. So if it is a standard normal distribution, there's no z-score really to find. You just look at the value. It is its own z-score. That doesn't happen very often. Okay? Just when we know we have a standard normal distribution. How do you know that? You're told. Okay? So we can find areas or probabilities for different regions under a normal model using technology or table A2. It says technology is strongly recommended. A TI 8384, you can use those if you know how to use them right, and for most of the stuff we do in here, you can pretty much whip out every answer, and there he is. I'm not going to teach you how to do that. The media assignments teach you how to do that, but I can help you if you are interested and you do somewhat understand how a calculator works. Anything a calculator can do, there are ways to do it out by hand. So I was telling you earlier about calculus and area under a curve. Instead of having to look at tables or punch things into calculators, you can use integrals and find area or find probabilities under a density curve. But we are going to use the table primarily. One question that I get a lot in my online class is, I have no idea how to work these problems. Where are they getting the numbers from? But they don't click on the table on the homework. Most homework problems are going to have a link to the table. The table is in A2. There's a lot of ways to get to the table. If you use the digital book, the ebook, yes, everyone has access to the ebook. If you have the ebook, you can find the table. If you scroll down and look at Appendix A, it starts out binomial probabilities. Go a couple pages in, and we're going to start, the table that we're going to use starts, it's table A2, so it's just a couple pages down. If you print out the formula sheet from the book, or if I've given you one, then you have the table. All right. Make sure that it says, I believe it says table A2 at the top. It is a standard normal distribution. Notice that it says cumulative area from the left. I've seen some tables for z-scores that don't give cumulative area from the left. They give a left side and they give a right side. Okay. For this table, any z-score that we look at under the standard curve, the area, or the probability here that we get, which is the area, will be cumulative from left to right. Okay. Again, this table gives area cumulative from left to right. You may not understand how big of a deal that is right now, but it is a big deal whenever you start looking at different types of problems. Okay? If the problem tells us we're looking for something less than, then that's the area cumulative from left to right. That's less than to the left of the z. If we're looking at something in a problem that says greater than, then we're looking for the area on the right side. How do you think you'd find the area on the right side of a z-score? If you know the total area is 1, and you can find the area cumulative up to that point, if you want to know the area on the right side of a z-score, you say 1 minus whatever you get in the table. We'll come back to that whenever we come to those types of problems. But it is important that you understand this table gives area cumulative from the left. All right, so there are several programs that you can use to find normal distribution areas. If you're looking at your formula sheet right now, that table that I was talking about that has area cumulative to the left, all of the numbers inside of the table, those are areas. So those are probabilities or areas. And all of those are to several decimal places. You can use StatDisk. I mean, there's hundreds of programs, but you can use StatDisk, Minitab. If you learn to use Excel, if you learn everything about Excel, you will be highly marketable. Excel is a very strong program, but it can do all of this as well. All right, the calculator, you can use the calculator. You know, it tells you different things you can do to find the area. But we're going to use the table. And again, all of these values in the table, these are areas. Now, how do I read the table? The first sheet of the table is negative values. Okay? Remember with z-scores, if you can remember back a couple chapters, we round z-scores to 2 decimal places. That's because, so we have 2 decimal places in our z-score. You say, well, I only see one here. That's negative 3.4. Well, the last decimal, the hundredths place, we have different columns. So if I wanted to look at negative 3.32, I go negative 3.3, and then come over to the 0.02 column. And so negative 3.32 would be 0.0005. All right, so if you're given a z-score, more than likely you're looking for an area or a probability. Now, whether that's an area left of the z-score or an area to the right of the z-score depends on the problem. So you can see for negative 3.5 and lower, that means negative 3.50 or less. So negative 3.51, negative 3.52, negative 10, negative 200. Any number less than negative 3.50, we use 0.0001. All right. And then if you look on your formula sheet, you'll see that the numbers keep going and going and going. They get closer and closer to 0. All right, so you see these numbers getting closer and closer and closer to 0. And then there's no such thing as negative 0. All right, at 0.0, you can see the area is 0.5. After this number, we go to the next sheet, the positive z-scores. All of the positive z-scores are still cumulative from left to right. Left to right. This is the area under the curve that would correspond to a z-score of, and it just depends on what the z-score is. So these are all positive. And you see those numbers get larger and larger and larger until you get to 3.50 and up. That means if it's a standard deviation, if it's a z-score that's larger than 3.50, we want to use 0.9999 according to the table. All right. Notice that on the table, on both pages, I believe, at the bottom of the table, you have some other numbers that are kind of highlighted here, and there are arrows that go to the table and show you where they are. I'm not going to tell you what those values are right now, but they are important. They're used a lot. So So there's numbers at the bottom of the negative z-score table and the positive z-score table that we will use a lot. All right, so our table says designed only for standard normal distribution which has a mean of 0 and a standard deviation of 1. It is on 2 pages. Okay. Each value in the body of the table is cumulative area from the left up to a vertical boundary above a specific z-score. All that means is, let me go back to the table. All that means is the table is cumulative from left to right. So if I look at this z-score, whatever it may be, 1.37, it's going to give me all this area here, up to 1.37 as a z-score. So if this was, say, a weight problem, I have one of those. I can't wait to eat. But if this was, say, the probability that a statistics teacher weighed less than 250 pounds, less than will always use a table. Less than means to the left of the z-score. So in the problem, if we're talking about less than, we're going to use the values we get out of the table. All right? But if the problem, say, was talking about greater than, the probability that a statistics teacher weighs more than 250 pounds, then we would want the area to the right of the z-score. And the way that you find the area to the right, since this is cumulative from left to right, is to say 1 minus the area to the left. Because we know that the total area under this curve is 1. So if I ever want to find the area to the right of a value, we'll have greater than in the word problem, and we'll say 1 minus. If we want to know less than, we want the area to the left. Less than to the left, greater than to the right. All right? So if we want the area to the left, we just take the value out of the table if we're talking about finding an area or probability. All right, let's move on. Not actually looking at an example, it won't make as much sense. So remember I told you the hundredth is at the top. So you do have z-scores at 2 places. All right, here is an example. Bone density test. This should be interesting to the majority of you out there. If not, you may be in the wrong profession. All right, a bone mineral density test can be helpful in identifying the presence of osteoporosis. The result of the test is commonly measured as a z-score, which has a normal distribution with a mean of 0 and a standard deviation of 1. A randomly selected adult undergoes a bone density test. Find the probability that the result is a reading less than 1.27. That's the key. Well, there are a couple keys on this problem, or keys to this problem. One is that the mean is 0, so normal distribution, the standard deviation is 1. That's important. Okay? And then we want to know the probability that the reading is less than 1.27. All right, so I told you if it is a standard normal distribution, that's when the mean is 0 and the standard deviation is 1, then the z-score equals, we said, x minus mu over sigma. And if it's a normal distribution, standard normal distribution, then x is the value we're looking at, so that's 1.27. We were told the mean was 0 and the standard deviation was 1. So if you subtract nothing from the value we're looking at, and then you divide it by 1, you just have the value we're looking at. So yes, that was a lot of meaningless work, but I want you to understand that with a standard normal distribution, the value that you have that you're looking at is your actual z-score. Okay. Now, we want to know the probability that the reading is less than 1.27. So here's what we do. We go to our z-score chart, and remember our z-score was 1.27. And we know the probability the reading is less than 1.27. So 1.27 is a positive number, and that's our z-score. So go to the table part that says positive z-score. Okay. Now, look on the left at the z. Go to 1.2. It was 1.27, wasn't it? All right. 1.27. 1.27. Now, this is the area cumulative up to a z-score of 1.27. 0.8980. All right. So if this was a z-score of 1.27, all of this area would be 0.8980. Now, since we want to know less than, we use the value we're given in the table. Okay. So the probability that it's less than is equal to 0.8980, or 89.8% chance. Now, if this problem would have said greater than 1.27, then we would still need to find this answer, but we would say 1 minus this answer. That would give you the probability that the reading is greater than 1.27. So less than, take the value from the table. Greater than, say 1 minus. All right. So here they're showing you, this is what we were finding, the probability that the z-score is less than 1.27. I know I use x, you can use x, you can use z for these standard normal distributions because they're the same thing. The value we got from the table was 0.8980. Remember, the total area under this curve is 1. So that 0.8980, here's the z. Oh, that's the area of all this. So that's the probability that this machine would read a reading of less than 1.27. Okay? That's what we found. Now it says, using the same bone density test, find the probability that a randomly selected person has a result above means greater than, above negative 1.00. So we want to know the probability that z is greater than negative 1.00. So let's look at our z-score chart. Let's go to the negative part of the z-score chart. All right. Now, we want to know the probability greater than negative 1.00. So we still need to look up negative 1.00. Negative 1.0, and then the first column is 0. We have an area of 0.1587. Now remember, this area that we have, that's cumulative from left to right. So if we want to know greater than, we have to say 1 minus the probability that z equals negative 1.00, or 1 minus 0.1587. All right? And I get 0.8413. So that's the probability that you would get a reading greater than negative 1.00. Kind of neat. So here are a few more examples. This is an important concept that some students grasp pretty quick, others don't. If you want to know the probability between two values, so this is the probability that when you got a reading, you would get a reading between negative 1.00 and negative 2.50. Since the table is cumulative from left to right, if we take the furthest one to the right, so we look at the 2, which one of these will be the furthest to the right? Don't just think because the number 2 is bigger, that's furthest to the right. It's not. You see, negative 2.5 is further to the left. So you take the one furthest to the right, that will give you the area up to that point. All right, then take the other, that will give the area up to that point. So the furthest one to the right, always, furthest one to the right, and then take your other one, and you'll say the area of the furthest one to the right minus the area of the other one, which will be the one furthest to the left. That will give you the area between the two. Sometimes students can't quite grasp that concept. Think about it like if you drive from here to here, but you want to know the distance from, say, here to here. You can take the total distance, and then you can subtract out, say, this piece. Or what if we wanted to know the distance between, say, A and B? We know the distance from A to B, so we wanted to know the distance from A to B. We know the distance from A to C, and we know the distance from B to C. Then you can just subtract the piece out that you don't want. That's basically what we're doing. If we want to find the area between, let me go back to the table. We want to find the area between two places, between negative 1.00 and negative 2.50. Take the one furthest to the right, take that area, then subtract the area furthest to the left, and that'll give you the area between. All right. So probability greater than, of course everybody knows the greater than symbol. There's between two values. There's less than. The main thing that you need to remember from about less than and greater than, less than to the left, take the value from the table. Greater than to the right, 1 minus the value from the table. Now we can, of course, use the area to find a z-score. All right? So if we wanted to find which z-score will correspond to the 95th percentile, and this is important, please take your table out, we're not looking for a z-score of 0.95. We're looking for the area that would come closest to 0.95. So let's say that I wanted to find the 95th percentile. That is the value that separates the top 5% from the bottom 95%. Then I can use a table to go to your z-score chart. Now we're looking for, since area in this table is cumulative from left to right, we're looking for the area 0.95. There's a chance we may not get exactly 0.95, but we want to select the area that will be the closest to 0.95. So if you start on the negative z-score chart, you can see 0.0. Well, we want 0.9, so we need to go to the positive z-score chart. The positive z-score chart starts with 0.5000. So keep going down, keep looking at numbers until you can get as very close to 0.95 as possible. Now, look here. This is 0.9495, and this is 0.9505. And there's a star between these two. Not all values you can see have a star between the two. So that must mean that that's an important value. 95% is an important value, right? It's a percentage that could be used a lot in the real world. So you can see, follow the arrow, down, 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 and over. What does it say the z-score is? Notice it does bring the z-score out to one more decimal place. That's okay, because it's a special value. So a z-score of positive 1.645 would be a z-score for the 95th percentile. Always. As long as it's normally distributed. All right, so you see that? Positive 1.645. All right, using the same bone density test, find the bone density scores that separates the bottom 2.5% and find the score that separates the top 2.5%. All right, so what we would want to look at, we want to know the z-scores, which are actually the x values, that separate the bottom 2.5%, the top 2.5%. Remember the way that these tables work. All right, if I look up, if I want to find this z, and we know the area is 0.025, that's 2.5%, then when I look up an area of 0.025, that will be this a negative z-score. It's actually negative 1.96, okay? Now, this is a little different over here to get this one. Notice that it's a positive 1.96. That's because of symmetry. But how would I get that? Because if I look up 0.025, I don't get positive 1.96. Remember, the area in these tables is cumulative from left to right. So if I wanted to find this positive value in my table, if I know that the area under this entire curve is 1, and I know that the area to the right of this positive z-score is 0.025, then I need to find in my table whatever 1 minus 0.025 0.025 is. 1 minus 0.025 is 0.9 what? 75. All right, so that's what you need to look up in your table to find this right z-score. Let's see. 0.975. Right there. So you need to figure out which column that was. I bet that's the 6th column. So that's the 6th column. And then 1.96. All right. So that's how you find those z-scores. The bottom, we would look at the value 0.025 as an area and then see what z-score it was. That would be negative 1.96. The top, to find this area, you have to say 1 minus 0.025 because the area in the table is cumulative from left to right. For a standard normal distribution, a critical value, a very important concept, is a z-score separating unlikely values from those that are likely to occur. A critical value is a z-score separating unlikely values from those that are likely to occur. The expression z sub alpha, that's a little alpha, lowercase alpha, denotes the z-score within area of alpha to its right. So, z sub alpha. A critical value is a z-score separating unlikely values from those that are likely to occur. The expression z sub alpha denotes a z-score within area of alpha to its right. All right, so for example, z sub 0.025. All right, that's the area to the right of the z-score. So if I wanted to look up that value, the area that I look at, remember, is 1 minus 0.025. So I'd look at the value, the area in the table, 0.975. We just did that, and we found that the value was 1.96. Okay. What if I wanted to know z sub 0.005? So this is the area to the right of the z-score. So I'd want to look for the area 1 minus 0.005, or 0.995. That's the value I'd want to look up in the table. So look as close as you can get to 0.995. And if you see right here, between 0.9949 and 0.9951, there's a star. The z-score is 2.575. Right, so that would be a z-score of 2.575. That is a special place there. That's a special critical number. What's the alpha? 0.005. Right, and that is the end of section 6.